Hi, and welcome to Failurology, a podcast about engineering failures. I'm your host, Nicole.
And I'm Brian, and we're both from Calgary, Alberta, Canada.
Thanks again, as we say every episode, to our Patreon subscribers. We really appreciate your support.
Nicole, how much does it cost per month for Patreon?
$5 Canadian.
That is less than the cost of a salad spinner.
Significantly less than the cost of a salad spinner.
Those things, not cheap.
No, and even though salad spinners are really fun to use, I think our bonus episodes are more fun.
And in those bonus episodes, you get to hear us talk about even more interesting engineering failures, and you don't have to eat salad.
And those episodes come out on the off week from these. So if you subscribe to our Patreon, you get episodes from us every week. And we have a special RSS feed for our Patreon subscribers so that you can listen to them in your regular podcast app. You don't have to bounce around to different apps. So please come check us out on our Patreon in our little corner of the internet and support our show.
This week in engineering news, non-invasive ultrasound therapy for the brain. Teams of engineers at the University of California, San Diego developed a device to enable non-invasive ultrasound-based therapies for the brain, which sounds super cool. So one example of this is sound waves used in trials to treat epilepsy, which is a great thing to treat. Epilepsy can be a very difficult condition for a lot of people. It significantly impacts their lives, as well as the lives of the family around them. So treatment of epilepsy or other diseases, brain diseases, is a great front to have new therapy options for. So while they're trying to target specific areas of the brain with ultrasound waves, they tend to bounce around and over-target some areas and under-target other areas, which can lead to hemorrhaging or overheating the brain tissue, which is not good at all.
No, definitely not good. I think we've come a really long way in biology and learning the human body and how different things function and how to treat various diseases and conditions and viruses, etc. But I think we have a lot to learn still about the human body, but specifically the brain. I think there's just a lot of things we don't know about brain injuries or various other types of conditions that impact the brain. And it's such an integral part of the human body. It's the piece that controls the function of pretty much everything. So it's a really important part. You want it to work well and work as optimally as possible. So, this research project is really interesting. So this non-invasive ultrasound therapy is using similar technology that concert hall designers use to make sure that everyone hears the music perfectly, to diffuse the ultrasound waves and distribute them uniformly. These uniform waves then simulate the areas of the brain that are sensitive to the waves and leave adjacent areas alone. So it allows them to dial in and target the areas that they want to target specifically while not impacting the adjacent areas that they want to leave alone, which I think is really cool and really important.
Yeah, and I believe over the last, I'm going to say 20 to 30 years, maybe longer than that, I believe cancer therapies have kind of gone the same route before, where they're able to target specific areas of the body or specific tumors instead of just targeting everything. And again, that's just, as technology has evolved and the understanding of things has evolved, a lot more that enables them to do all of these really cool things on the medical side that we get to learn about. And sometimes I know some of the words, which makes me feel super awesome.
Yes. Same. Sometimes when we're researching these engineering news topics, we look at articles, the headline sounds really cool, and then we read it and we're like, I don't know enough of these words to repeat them on the podcast. And so we have to be a bit strategic about which ones we talk about.
Or I'll reach out to friends in the medical field and they'll get back to me a month after the episode airs. They're quite busy people. So we just kind of file them away for in the future, maybe we'll talk about this thing.
Yes. So if you want to read more about this study about non-invasive ultrasound therapy for the brain, check out the link on the webpage for this episode at failurology.ca.
This week's episode of Failurology is brought to you by CRISPR. Not the genetic engineering technique, but your vegetable CRISPR.
Actually, this isn't a sponsor. It's a PSA. You should probably clean out your vegetable CRISPR. There's definitely a cucumber or a box of mixed greens you bought last week or last month or last year that needs to go?
We're not here to judge. We can't see your fridge. We won't even know whether you cleaned it out or not, but you'll probably feel better if you do. Now on to this week's engineering failure, the Interstate 35 West Bridge over the Mississippi River in Minneapolis, Minnesota. The bridge's official name is Bridge 9340 and it's located just west of downtown Minneapolis. The bridge was an 8-lane steel truss arch bridge that crossed the Mississippi River 875 meters downstream from St. Anthony's Falls.
So I was in Minneapolis in 2019.
Hey, so was I.
Oh, fun. What were you doing there?
I was there for a funeral, so it was not that fun.
Oh, that's not. Yeah, I was there for a Vikings game.
No, I went to a Twins game when I was there, but the primary purpose of my trip was for a funeral. Going to a Vikings game sounds like a much better reason to be in Minnesota or in Minneapolis. I quite like Minneapolis. I think it's a great city.
Yeah, it was a really good trip. The Vikings fans that's American football. They're pretty hardcore and they like to yell and scream a lot inside the stadium, which makes it really loud, which I really enjoy. I thought that was fun, a fun experience. And I'm pretty sure they won, but it's been a long time. I'm not necessarily a Vikings fan. I just like to tour around and check out different stadiums and different sporting events. So I usually root for the home team wherever I'm at. I'm actually a Broncos fan. Go Denver. Anyways, back to this episode. So I was in Minneapolis in 2019. Apparently so was Brian. And there's a pedestrian bridge there called the Stone Arch Bridge that crosses the river between the falls and what is the replacement bridge for the one we're going to talk about today. It's actually a really, really cool area going across the river. And I didn't quite realize when I was there how close to this collapsed bridge, the I-35 West Bridge over the river, was to where I was walking and traveling around within Minneapolis. And so when I started researching this episode, this bridge failure is popular is probably not the right word, but it is a somewhat well-known failure. And so I had known about it for a while. It was on my radar pretty early on when we started the podcast, and it's been on our list for a while, but I wasn't really sure where it was in Minneapolis. So once I started, as I do, looking at the maps while researching this episode, I realized that I was pretty much right next to this bridge, or at least the replacement bridge, which I always think is really cool. As much as I really like looking up these failures on Google Maps and seeing the area and the geography and where these are located, having a in real life reference, having been to that location or going to that location after the fact adds an extra layer to the story for me personally. Also, that said, so this bridge that, as I said, is located between Falls and what's now the replacement bridge. And I thought those falls, they're called St. Anthony's Falls, were man-made, but they're actually the largest natural major waterfall on the Mississippi River, which is pretty cool. Also, fun fact, the Mississippi River is the second longest river in North America, and it travels over 3,500 kilometers from the northern part of Minnesota all the way to the Gulf of Mexico. And we've talked about the Mississippi River on other episodes, not necessarily the river itself, but it's been, adjacent to other failures that we've covered. It's a long river, travels through a lot of states, and it's also very cloudy. It picks up a lot of debris. So it's not a river I'd swim in. That's for sure.
For anyone wondering, the longest river in the U.S. is the Missouri River, which I believe is about 2 kilometers longer than the Mississippi River. And then I think it's the Yukon River that's the third longest river, but it may be the Rio Grande.
Very cool. Very cool.
Bridge 9340 opened in 1967 and carried 140,000 vehicles per day, which sounds like a lot of cars per day crossing this bridge, but it is an 8-lane bridge, so maybe that's in the right ballpark for a fairly average 8-lane bridge.
That said, though, Minneapolis, let's assume approximately 1 million people live there. This bridge is still servicing a significant amount of the population. It's an integral part of the infrastructure. It's right outside of downtown. It's likely used by a lot of people for commuting. So this bridge is really, really important to the city and the functionality of the city's infrastructure. Having this bridge collapse has a huge impact on Minneapolis.
Yeah, it's bad enough when any bridge collapses, let alone a bridge that is 8 lanes wide and carries this many vehicles per day. That makes a significant impact on other arteries and other bridges that go into downtown or go out of downtown. So this is a significant collapse of this bridge. And that collapse happens on August the 1st, 2007 at 6:07 p.m. and unfortunately it kills 13 people and injures 145 people. The bridge had been in use for 40 years at the time of the collapse. The bridge was also undergoing some lighting and railing upgrades, and while 4 lanes were closed, there were 260,000 kilograms of supplies and equipment that were on the bridge.
So I'd just like to reiterate that the bridge is 40 years old at the time of the collapse, and we'll get to this, but there was definitely some deterioration of the structure over that time. But important, and we will call back to this later, half of the bridge was closed, 4 of the 8 lanes were not in use, and on those closed lanes were 260,000 kilograms of supplies and equipment.
The National Transportation Safety Board investigated the collapse and noted that the likely cause was the design flaw of a gusset plate that was too thin and ripped along a line of rivets. So a gusset plate, for those of you who don't know, it's where beams or girders fasten to columns by way of bolts, rivets, or welding. So it's just a plate that kind of connects 2 pieces together via bolts or rivets or welding or some sort of method to join 2 pieces together.
Yeah, and for further explanation of that, if we refer to beams, columns, girders, etc., as structural members, the beams or girders are the ones going horizontally or parallel to the river, and then the columns go vertically or perpendicular to the river. So it's where the horizontal piece of the bridge connects to the vertical portion that goes down to the foundation along the arches, of which there were 14 spans. 14 horizontal sections in between columns that extended 580 meters across the Mississippi River. The 3 main spans were deck truss construction, while the middle span, being the longest, was 140 meters over the 119-meter river crossing, meaning that none of the piers were located in the water. 9 of the 11 approach spans were steel multi-girder construction, and 2 were concrete slab construction. So the approach spans are basically the on and off ramp to get across the bridge. And then the longest span in the middle was the one that actually crossed the river. Depending on how they're constructing all of the different components, they don't necessarily use the same method for all of the spans. So 9 of the 11 were steel girder, and the rest, the 2 main spans, were concrete slab construction. And the roadway deck was approximately 35 meters above water level. So interesting story about Pier 6, which is the pier at the south end of the longest span over the river, so just on the south side of the river. One of the original contractors who was going to build the bridge expressed concern that Pier 6 couldn't be built as planned, and after they tried to negotiate alternate options with the Department of Transportation, that contractor actually backed out of the project altogether, which I think is really interesting and something you don't necessarily see all of the time, or at least you don't hear about it all the time. So the contractor fundamentally disagreed with the design for Pier 6. And they tried to negotiate an alternate solution, and they were not able to. And so they said, we don't want to build it like this. We don't think it can be done. They didn't want to accept whatever potential risk could come along with it. I'm assuming that was their concern, is they're taking on added liability and risk by building something they don't think will work. And so they decided not to go forward with the project, which, again, I think is really interesting. It's not something you hear about all the time. A lot of times it's just, a lot of times people negotiate the different components of the design. Of course, there's usually value engineering or cost savings that they're trying to negotiate, or constructability. As we've seen with other bridge collapses or other types of, especially it seems structural failures seem to come across this often. Not picking on structural engineers, I know this theme has come up more than once, where the structure is designed as a complete structure, and there's not always adequate consideration for how that structure is going to be put together. And what I mean by that is you may have certain spans that need to support themselves until the next piece can get constructed, and they don't always allow for that span to self-support as part of the construction process. So in addition to that, on December 19th, 1985, there was a large pileup caused by black ice when the temperature reached minus 34 degrees Celsius, which is pretty close to minus 34 Fahrenheit. Minus 40 is the same in both units. Due to the proximity to St. Anthony's Falls, which obviously are creating quite a bit of mist and humidity in the air. The bridge was highly susceptible to an almost frictionless thin layer of black ice. Black ice is really dangerous. You can't see it until you're sliding on it. So it makes driving in the winter potentially really unsafe. And so you have to drive pretty defensively when there's risk of black ice. But of course you can't see it, so you don't know that it's there until you're on it. And then again in October 1999, the Minnesota Department of Transportation embedded temperature-activated nozzles in the bridge deck to spray a potassium acetate solution and prevent ice from forming. Essentially, when the bridge got below a certain temperature, they would spray this potassium acetate solution on the bridge to prevent ice from building up and creating a dangerous scenario. And although not proven during the investigation, it's thought by some that this potassium acetate solution may have contributed to the collapse by corroding some of the structural elements. So that's just a theory. It wasn't proven in the investigation. That said, I don't know how closely they looked at it. I obviously wasn't part of the investigation. We're just looking at the report after the fact, and that wasn't noted as one of the findings. I do think it's an interesting component, especially if that potassium acetate was looked at as a solution just for ice without considering the other impacts. And potentially they looked at how it would react with the road surface, but maybe not some of the other components that that solution would eventually reach by seeping through cracks and various other exposed pieces of the bridge. Yeah, I can't really say for sure how much of a factor that had, but I do think it's an interesting component of the bridge.
Yeah, so the bridge had been annually inspected since 1993, and in 1990, the bridge was given a rating of structurally deficient due to significant corrosion of bearings.
That's 17 years before the collapse happened. It's labeled, quote, structurally deficient, which is not good.
That's not a good rating to have on really anything, and certainly not on bridges that are carrying any people or part of your infrastructure, part of your daily commute. You don't want something that says structurally deficient coming up on your daily commute that you rely on to get to and from your job or to see friends or just you need to get around. And so in the US, there's 75,000 other bridges that had this classification in 2007. Now, I'm going to go out on a limb and say that there've probably been more bridges and other structures added to this list in the intervening 15 years. They may be over 100,000 now, certainly more than 75,000. Most of these bridges and other structures are probably still in operation, and they're going to need significant repairs, and they're currently still there, still doing their thing for now.
For now. This is a big problem, in my opinion. And yeah, we're picking on the States right now because that's where this bridge is located. But this is a problem in a lot of countries. Bridges are expensive and there's a lot of capital cost that goes into constructing them. And yes, they're looked at and there's maintenance that happens, but they seem to be overall neglected as a whole. And there just seems to be this theory that the bridge will just be there forever, but it won't. And I think it's a critical piece that we're missing in maintaining these bridges and correcting and fixing them and repairing them as needed to keep them functioning above the status of structurally deficient. I don't know what the next level is, structurally acceptable, but they all need to be brought back up to that level. This is not okay.
Yeah, and if bridges collapse, they have a significant impact on people's ability to go to work and generate revenue and GDP for things. So I feel it's in the best interest of countries to maintain all of their bridge and their road infrastructure so that their commerce side of things, all the big heavy trucks and all the people going to work, that side can function. And I think in the States, we saw a lot of bridge building, kind of in the 50s and the 60s as part of, interstate highway projects and, as giant transportation projects. And those bridges, they're getting a little old. I mean, just like people, the joints start to not be good and they start to break down and wear out a little bit. So they need some remediation so they can keep functioning the way that they were intended to function. In 2001, the University of Minnesota's Civil Engineering Department studied the bridge. Cracking had been discovered in the cross girders at the end of the approach spans, and there was resistance to motion at connection points where the main trusses connected to cross girders was causing the bridge to distort out of the plane, which was causing stress cracking. So there were some things going on with this bridge that were not ideal at the time in 2001 when the University of Minnesota did their study. To combat this, they drilled the cracks to prevent them from spreading and added support struts to the cross girders to prevent more out-of-plane distortion. So they've done some mitigation. They've kind of passed this problem into the future, made it a future problem instead of a current problem. It's still something that needs to be addressed, but this is kind of a stopgap measure before they do any more significant work. It's kind of like repairing the crack in your windshield or the little chip in your windshield before it becomes a giant crack in your windshield.
That might be a reference only the Albertans get.
No, there's lots of people that have windshields they need to replace every year, right? Right?
I don't know that other areas of Canada use gravel as their snow control method. Most use salt, but it's too cold here. Saskatchewan would understand. Manitoba for sure, but BC, Ontario, and East, I don't think they know what that means.
Yeah, so our cars here in Alberta, they don't rust. We just replace our windshields once a year.
Yes. Well, not necessarily once a year, but yes.
More frequently than other jurisdictions. Going back to the University of Minnesota report, this report flagged a lack of redundancy in the main truss system. And if you've listened to this podcast for a couple episodes or all of the episodes, or even if this is your first episode listening, we talk a lot about redundancy on past episodes. It comes up almost every episode. The importance of having redundant things built into your systems, or redundant controls, or just over designing things. Having redundancy is always good. In bridge design, it means that the failure of one member would not lead to the total failure of the bridge. That there is redundancy in the structural members such that failures of one member transfers loads to the other member to carry it until the bridge can be repaired. And we've talked about this sort of redundancy with other bridge episodes, and we've talked about it with other structural episodes, where if one thing fails in your design, the rest of your design shouldn't collapse or cease to exist or fall down. It's important to have redundancy.
And I think the worst example that's coming to mind right now that we've covered is the Florida pedestrian bridge, where failure of any member, really, not just one specific member, but any member, collapsed the entire bridge. Also, the Hyatt Regency walkway that we covered, that one was one of the earlier episodes. I think it was episode 3 that we covered. It also had some significant redundancy issues. Mind you, they were trying to hang 2 bridges from a design that was only intended to hang 1. But also, yeah, significant lack of redundancy on that one. Yeah, like Brian said, it's something we've talked about a lot. It's really, really important. I think especially in structural design, it's really, really important. But even in mechanical design, which is what I deal with every day, we're often building in redundancy. We don't design a heating system for the bare minimum. We design it for, a safety factor. And then on top of that, there's usually multiple boilers or multiple devices that create hot water or whatever the heating method is, so that if one of those items fails, heat can still be generated in the winter, because there's nothing worse than a building in -40 weather that doesn't have heat. You don't want that. You don't want that. It's bad news for everybody, especially for the people that live there. It's not good. So yeah, redundancy is really, really important.
Yeah, and redundancy should be a part of pretty much everything you do in your life, not just engineering things, but if you plan everything where it's going to work exactly the way it needs to work, you're going to probably have a lot of disappointment at some point in your life when things don't go quite right. So redundancy is good. Redundancy is even better in bridge and structural design. In 2005, the bridge was again rated as structurally deficient and in need of replacement, which is shocking because they didn't do anything to address it since 1990. I'm not sure how they got the same rating without doing anything. The sufficiency rating is a score out of 100. Bridge 9340 received a score of 50. Just for reference, only 4% of heavily used bridges receive a score of 50 or lower. But since this bridge was deemed to have met minimum tolerable limits to be left in place as it is, they didn't close it. This is not going well for this bridge. It's basically in the lowest 4 percentile of heavily used bridges. If you're in that scoring region of things, you're not doing a very good job at what you're supposed to be doing.
No, definitely not. And I think what sometimes happens is that We as engineers think that something's in bad shape and it should be replaced, but maybe it's okay for a little while longer. Cuz you can't predict when something's going to fail. So you think, okay, yes, these repairs need to be addressed, these components need to be replaced or strengthened. You provide all those recommendations. So there may be this assumption from the report that they have a little bit of time to make these repairs. And the owners of this infrastructure don't react with the urgency that they need to. And I get it, you can't necessarily be the boy who cried wolf, and you can't say everything's going to go wrong all the time and come out really, really strong on your reports. But I do think that it's important to use firm language when talking about failing systems to stress to the reader that something needs to be done. And sometimes you have to say, this is going to fail right away for them to react and actually fix something.
I think the other thing too that makes it a little difficult on the bridge repair side or the infrastructure repair side is a lot of these projects require, either federal funding or state level funding, or you can have a higher level government funding. And running on a campaign of fixing bridges is not exactly the greatest political slogan to run under. People a lot of times just accept that the bridge is there, the bridge works, the road is there, the road works. Or until it collapses, it doesn't really come to the forefront of kind of the public awareness or public consciousness. So sometimes with bridge repairs that are needed in the future, it's a problem that gets kicked down till the next election or the next government, or the current government doesn't want to spend the money because they're on a campaign of reducing money or reducing spending. And unfortunately, all this stuff kind of just lingers in the background until it fails, like we've seen in this bridge collapse.
Yeah, I think politicians don't want to run on a campaign of, we're going to fix this thing that you think is fine and is already working.
Because that costs a lot of money.
Yeah, and so to the end user, it feels like they're not really getting tangible results, or that their dollars are being well spent, because they don't see all of the risks that are going on with the bridge. I assume a lot of the reports are available to the public if requested. But again, it does feel like you're getting kind of shortchanged a little bit. And I see these failures, and I still would probably feel a little bit of that. Although when you look at how many bridges, I mean, we're talking 75,000 bridges in 2007 were, quote, structurally deficient in the United States. So when you start to look at the statistics and dig into it a bit more, it is pretty easy to see that this is money well spent. But sometimes it feels like we're so far behind on things that need to get done that you don't want to spend the money on things that are already functional, but it obviously is necessary.
Yeah, actually, just to follow up on that, there's a bridge that I can see from my condo. It's a couple hundred meters away from my condo that crosses the main river in Calgary here. And a number of years ago, I believe there was a corrosion issue they identified that was going to cause some structural issues with it. And it got funded, and the project was eventually completed. But over the year or so that it took them to finish the bridge or to complete all these repairs, a lot of people just saw it as they were closing one or two lanes of the bridge, and they couldn't see any improvement for it, because a lot of this work was going on underneath the bridge, or it was going on after they ripped up parts of the lane. So as a person that just drives over the bridge, you may not see the work that they're doing or understand the significance of the work. All you see is that they're increasing the time on your commute by 10 minutes or 15 minutes, and there's no visible tangible results. But if this work wasn't done, there was a strong possibility that this bridge would collapse over the next number of years, or be completely unusable. And that would significantly impact people in this case coming out of downtown. But again, it's a key transportation link out of downtown Calgary, kind of in the same way that this bridge was a key transportation link out of Minneapolis. So the bridge repairs are done, and visually it just looks like they did some cement work, and they put a new railing in, and they changed out the streetlights that were on the bridge. But there's so much more work that went on underneath the bridge, making sure that it was structurally sound, and dealing with corrosion, and dealing with a whole bunch of other issues that you couldn't see from the bridge. Back to the bridge in Minneapolis, it was inspected again in 2006, and was expected to be inspected in the fall of 2007. I'm going to keep going on the collapse itself, which happened in 2007, and we'll circle back to the 2006 report in a little bit. On August 1st, 2007, the bridge collapses. It's the day after the collapse. August the 2nd, the governor said that the bridge was scheduled to be replaced in 2020, which is at least 13 years too late at this point. Interestingly, a reinforcement project was planned for December 2006, but was canceled a month later after engineers realized that drilling into the bridge would actually weaken it. Also interesting, during the investigation, internal documents within Minnesota's Department of Transportation talked about the risks of the bridge collapsing, and they were worried they might have to condemn it, but they didn't. So this bridge was not doing super well.
No. And to an extent, I mean, I kind of get their stance. Just hear me out. Based on what the bridge serves, there would have been a complete uprising if they closed it without any immediate plans to replace it. That doesn't make what they did okay, but I kind of see that it was easier to just ignore it and hope that the bridge makes it through rather than closing the bridge without any plan to do anything about it. And, you know, being an engineer, you're often the bearer of bad news, which does kind of suck. I like to try to help people, and that does kind of cancel out the bad news part, but I often do have to tell people bad news that they don't want to hear. So I kind of get it. I don't think it's okay. And this obviously isn't the decision that I would make. I would probably have closed the bridge and said, well, it might collapse and I'm not dealing with that. Like, I'm not going to take on that liability or risk. It's not worth it. But unfortunately they didn't, as we've seen. So when the bridge collapsed, the central span over the river gave way first, followed by the adjoining spans. The south part of the span shifted 25 meters east or downstream on the river as it collapsed. So looking at photos of the collapsed bridge, it looks like every span pretty much collapsed, and it actually looks like the entire bridge just kind of dropped onto the river. You obviously couldn't still drive across it, but I think one of the reasons there were relatively few deaths for being a full bridge at the time was that all of the cars just kind of dropped with the bridge, and very few actually fell into the water. So it wasn't a case of some of the spans collapsing and breaking away from the bridge. The entire bridge kind of went down together. And every single piece of the bridge collapsed. So this is pretty much the definition for catastrophic failure. Every single part of the bridge gave way. And the collapse was also caught on camera from a nearby security camera, which is pretty interesting that you're able to actually see it collapse. That's not often the case that you can see the collapse happen on video. So as I mentioned, the bridge wasn't submerged into the river when it collapsed. So looking at the photos, you can see pretty much the entire deck sticking out of the water. And a lot of the vehicles are still on top of the bridge deck. There were a few that were submerged. And of course, people were still severely injured and access to them was challenging. But I think because the entire bridge kind of collapsed altogether, the devastation was less than it could have been. Not that it's okay. It was preventable. It was completely avoidable, but it could have been worse. And that's something we've seen on other episodes too. So as promised, I'm going to circle back to that 2006 inspection because it was fairly extensive and it happened just months before the collapse. The bridge was designed in accordance with 1961 standards, which was revamped in 1974 to include a completely different fatigue design method. The code was changed shortly after this bridge was constructed, and unfortunately it didn't use the upgraded fatigue design methods that were required in the updated code. So during this 2006 report, they made the following recommendations: that 5 main truss members in one half of each truss, which represented 20 members in the entire bridge, were identified as fracture critical, meaning that a fracture would result in failure of the member, and based on the lack of redundancy that we talked about, would also likely result in failure of the bridge. These members should have been retrofitted with steel plating to add internal redundancy to the member and would have reduced the possibility of failure of that member and then, of course, the entire bridge if the fracture were to develop. There were some pretty significant potential truss failures that were occurring in this bridge. Every truss had a weakness, which represented 20 members across the entire bridge. And remember, this bridge has 14 spans. So that's a lot of potential failures that we're talking about here. It's a significant portion of the bridge structure. Further review of some of the weld locations should have been further inspected with access hole cover plates removed. And this meant that the covers were not removed as part of their regular inspection process. Who really knows how long it had been since they were inspected? And the risk that you're undertaking by not fully inspecting all of the bridge components, by not uncovering them all to actually be able to see them, is that you're not aware of how extensive the corrosion is underneath the bridge. This bridge is, one, it crosses a river, two, it's right downstream from a waterfall. This bridge is seeing a lot of humidity and likely susceptible to a lot of corrosion. And so I think it's really, really important to get a good look at all of this critical joints and connections on the bridge, such as these welds that were covered, so that you can see just what potential risks there are. And they just weren't doing that. And that is also something we've seen before. It's actually fairly common, which is unfortunate. The bridge deck also should have been replaced with a lighter continuous deck through the main truss spans and a composite truss system to reduce the live load and improve redundancy. So to keep symmetrical loading during deck placement, the report also recommended that a more detailed analysis should have been done on the loading impact before the deck replacement had proceeded. So the deck, the part that you drive on, had been replaced a few years prior, and they at that time had an opportunity to install a lighter composite system that would have reduced the load on the bridge, and they unfortunately did not do that. The report also found, surprise, surprise, that corrosion was in a lot of localized areas near the deck joints. Not surprised. The bridge sees a lot of humidity from that waterfall that's right upstream. So none of the previous inspection reports that had been done on this bridge over the last 40 years, as well as on 700 other bridges of similar construction, none of these reports had caught that the gusset plates were undersized. They were 13 millimeters thick. They should have been much thicker. They were, again, how the beams and the columns attached to each other to carry that load from the horizontal deck down to the piers and the foundations of the bridge. Those gusset plates were not properly sized for the load of the bridge. And unfortunately, no one who had been inspecting this bridge caught that on this bridge or several other bridges that were of similar construction. What's especially interesting about this is that a photo from 2003 showed that some of those gusset plates were bowed, and they were also severely corroded. When you have structural members that are starting to bow, that's the time hopefully before then, but at least at that time, you should stop and say, hey, that's not supposed to look like that. I wonder what's going on here, and start to dig into it a little bit more. And had they done that in 2003, they would have had lots of time to make these corrections before the bridge collapsed 4 years later. But unfortunately, that was not the case. So while the gusset plates were undersized for the bridge loading and they were bowing in 2003, they were actually oversized when the bridge was originally designed in 1967. But the loads on the bridge had increased over time as the usage changed. More cars were added, the deck was replaced, and that included 50 millimeters of concrete that was added to the road surface, which increased the static load of the bridge by 20%. So while the gusset plates were the ultimate cause of the failure, they were undersized for the load at the time of the failure. They were bowing 4 years earlier. They were actually designed correctly back in 1967. But if you remember, the design requirements changed following the construction of this bridge. And so I believe the gusset plate design was increased as part of those changes, but that didn't impact the bridge because it was already built, and it was what we call grandfathered to the older code.
So what happened as a result of this? Well, chances are there's probably a lawsuit. Turns out there was a lawsuit. In May of 2008, a $38 million fund was set up for the victims of the collapse of this bridge, and in August 2010, the lawsuits were settled for $52.4 million. The company that designed the bridge, actually more specifically the company that bought that company, was also sued by the state of Minnesota, and they ended up settling out of court for $8.9 million. So in Canada, liability is typically 10 years, but under extenuating circumstances such as these, I'm not really surprised that they were sued 40 years later. This is a significant failure of things that shouldn't have failed this quickly. And there was significant loss of life and injury that occurred from this. So I'm not super surprised that they were sued 40 years later. I do assume, though, that the engineer of record for this bridge, he is probably not practicing, possibly not alive At this point, if you're going to be the engineer of record for a bridge, you probably put some time into your career already. If this collapses 40 years after you've designed it, may or may not be here currently. The replacement bridge was built in the same place and it opened in September of 2008, a little over a year after the collapse, which is pretty impressive as these projects usually take many years to complete, with the design stage and then the tender stage and then the construction stage and the commissioning stage. Bridges, especially 8-lane bridges, or bridges that would carry this level of traffic, they seem to take forever to complete.
Yeah, I will say, had the bridge not collapsed and had the replacement bridge not been needed immediately and not gotten the attention that it did from the collapse, it probably would have taken them a year just to secure the funding, another year for the design, and then 3 years-ish for the construction. So the fact that they were able to get this done in a year was really, really impressive.
Everyone here has been to cities or lives in a city or you've seen bridge and road construction. You know it never takes a year to finish anything. It's always a super long time to finish anything. So a year to build a bridge, and not a tiny bridge, that is incredibly quick. The bridge was done as a design build, which simply means that the contractor hires a consultant team and they operate as one team to design and construct the bridge. It's a fairly common method for infrastructure projects. I think it's fairly common on the projects that Nicole works on. I've certainly worked on a number of design build projects like this. So this does reduce a lot of the paperwork and red tape, and it allows for fairly effective, actually I think it allows for really effective communication between the designers and the contractors. There's less people to go through. The game of telephone is much shorter. It's a much shorter string to get all the decision-making people involved.
I think too, in standard construction process, which is where the owner hires the consultant team, the architects, engineers, etc., and then also separately hires the contractor, the general contractor who hires all the subcontractors. There's this perception that everyone's representing the owner and working together to complete the project. I'm just going to preface this by saying that's the way I approach the project, but it's not very difficult to go down a path where the two sides almost work against each other or fight each other. And I don't think it's deliberate on anyone's part, but I will say that design builds are a lot more collaborative. Everyone works together a lot better. And the other part that's beneficial is the contractors at the table day one. You're not finishing the design and then the contractor's like, okay, but can we change these 5 things? You already know what they want before you even go in. And so you already have, you know what type of equipment they're going to use. In this case, what type of bridge they want to build, what they're good at, what their strengths are, what materials they can get, what their budget is. And so then you're kind of reverse engineering backwards to make sure that you've got all your loads captured and you're designing for all the components that you need to. But I just think it makes a much smoother process when everyone's working on the same team and all the players are at the table day one.
It makes a huge difference, especially on large projects or projects that take multiple years. I've had projects where we've done a ton of design work. We thought everything was good and it looked good on our end, and we kind of had a contractor in mind or kind of, abilities that they had. And then it wound up going to a different contractor that had different views on how they wanted to construct things, or they were going to use different materials. And it didn't set us back to step 1, but it set us back to like step 1 3/4. There was a lot of rework that had to be done. It pushed out timelines that were already super tight. We were already, over budget or over timeline on some of them. But having the contractor, like Nicole mentioned, kind of having everyone at the table from day one, that makes a huge difference on people being on the same page, and contractors can have input early on. The owner can have input early on. You're not basically presenting an entire package to a group that's never seen it, because in a design build, they've been involved since day one or, week 1 or month 1 of the project. So I find as well that they go much, much smoother the earlier that you involve all the people that are involved in the project.
Yeah, I will add one more thing with design build. When the contractor's hiring the consultant team, they're typically hiring consultants that they've worked with before, that they work well with, that they communicate well with, that they like working with. And that's not to say they're playing favorites. It's just when I've worked with someone before, they know what my expectations are. I know what their expectations are. We know strengths and weaknesses. We know how to fill those gaps. And so again, I'm not playing favorites. It's just when you have that relationship, that working relationship, you've worked together on other projects, the communication and the entire project just does go a lot smoother. I'm a big fan of design builds, in case that wasn't clear. Big fan.
Yeah, I like collaborative projects. There's stuff that I'm really good at, and there's stuff that I'm really bad at. And when you have people that are really good at the stuff I'm really bad at, it makes the whole project go so much smoother. And if you've worked with these people in the past in previous projects, like Nicole said, it just makes things go so much smoother because you know how they communicate, and you know various people on their team. You know what they're good at, what they're maybe not as good at. There's not as much of a discovery process. Early on you can just kind of sit down and get to work, and people know what they need to do, what the expectations are, who they're reporting to, what's going on, how the teams are going to interface. I really like design build projects as well. Speaking of which, on the efficiency side for design build projects, the replacement bridge finished 3 months ahead of schedule and received an award for Best Overall Design Build Project Award from the Design Build Institute of America. So that's pretty awesome. So there you have it, the collapse of Bridge 9340 in Minneapolis, Minnesota. A design flaw, changing needs over 40 years of operation, and bridge inspections that could have been better led to the collapse of the bridge during rush hour on a summer day in 2007. The US specifically, but really every country, needs to take better care of their aging infrastructure to prevent catastrophic failures.
For photos, sources, and an episode summary from this week's episode, head to failureology.ca. If you're enjoying what you're hearing, please rate, review, and subscribe to Failureology so more people can find us. If you want to chat with us, our Twitter handle is @Failureology. You can email us at thefailureologypodcast@gmail.com. You can connect with us on LinkedIn, or you can message us right on our Patreon page. And if you reach out to us, we will respond. Check out the show notes for links to all of these. And thanks everyone for listening. Tune into the next episode where we'll talk about Chalk River Nuclear, a laboratory site upstream of Ottawa that was the location of 2 nuclear accidents in the 1950s. Bye, everyone. Talk soon.